How does it? Okay, so back for. Okay.
Okay, so for the last talk of the morning, we have Vincent Vargas from Geneva. The title's up there, Liouville CFT from probabilistic construction to Bootstrap solution.
Okay, so thank you very much for the invitation. So for me, it's a kind of odd experience because I'm talking in front of, I don't know, maybe 100 people. I don't think I met any of you except maybe one or two before this talk. So I don't know what to expect or what you expect from this talk, given the fact that I don't know how many times a probabilist has taught at string math. And so I'm a probabilist, and I'm going to talk about a project that I've been working on for the past 6 or 7 years with lots of colleagues. So in the beginning we were working with François David, who you must know, who is a physicist, Kupiainen, a math physicist, Rémi Rhodes, a probabilist. And we were joined lately by a bit after by Guillarmou and Guillaume Baverez. So we're kind of building all this framework. I'm building this framework for all these people. So what I'm going to try to do today is kind of explain what we're doing and what is the goal of our work, and try to convey a few messages to people who are not familiar with probability theory, and maybe I'm going to try to highlight what probability theory can bring to these problems related to string theory. Okay, because I'm going to be talking about a conformal field theory, which was actually introduced in the context of Polyakov's approach of string theory. So first, let me give you a bit of a context. So on one side, you have statistical physics. So say it in 2 dimensions at criticality, or so this can be described by using probability theory. So on one side, you have statistical physics, probability theory, and on the other side, you have conformal field theories. And in the modern approach of conformal field theory, you work within the framework of the celebrated conformal bootstrap, which was introduced by Pelavin, Polyakov, Zamorochikov in 1984. So behind this framework, this very powerful framework, you have, the keywords are representation theory, which people here are more familiar with, and also there's words like recursive procedures, etc., crossing symmetry constraints. So there'll be a talk on this tomorrow, I think, by Mazak in certain contexts. So it's a very powerful method which has been used also in 3 dimensions, etc., etc. And basically, the goal, one of the big issues in math physics is to relate statistical physics or probability theory to these conformal bootstrap approaches of physics. This is, and there are still huge open problems in this field, and so a bit after these BPZ axioms, so people started writing math axioms to try to really formalize this BPZ framework, and I gave a few here. So there's these VOA, vertex operator algebra, which were introduced by these people, and then there's the axioms which were introduced by Gavitsky, Kontsevich, Segal, which are more geometric flavor. And today's talk is going to be about relating, okay, one model, say, of statistical physics to the bootstrap via using these math axioms, which will show us how to get there. So, so as I said, statistical physics are usually described by Gibbs measures. So you just, when you have a configuration, you just give it a weight and say you renormalize to have mass 1, you get a probability measure, or, which will be the topic today, you work with continuum model, which is a Feynman path integral. Okay, so the problem is when you work with continuums, continuum Feynman path integrals, they're not always easy to define. Okay, and actually, probably the biggest problems in math physics are about defining some Feynman path integrals. but it's one of the natural ways of doing quantum field theory. And so when you have these continuum objects, so formally it's a volume form on the space of functions on a manifold. So I'll be only talking in 2 dimensions today. So you take a Riemann surface and you're trying to put a volume form on the space of all functions defined on this Riemann surface. And a way of describing your system is through correlation functions. So usually what you have is a bunch of fields which are indexed by, say, some subset alpha. And if you want to understand your Feynman path integral, you want to compute the correlation functions. So say, let me take so you have a surface, okay, a genus 2 surface, and you have points on your surface and you put weights. So point x1, weight alpha 2, alpha 1, sorry, etc. So you put points on your surface, okay? And to this thing, you put fields, and so you associate correlation functions. So here it would be this, right? On your surface, and it's going to have a metric on it, metric G. Okay? And then you put a metric on it. Okay, so and so I mean there are different ways. So if you try to do, define these objects, so by using Feynman path integrals, I mean you're faced with this problem of defining the objects in a mathematically rigorous way. And so these other, so there's, so sorry. Okay, so inspired by this path integral, so Segal, he wrote axioms. Okay, so he said, imagine you have a quantum field theory, and imagine that you can define correlation functions using this path integral. Inspired by this, he derived a set of geometric axioms that a conformal field theory should satisfy. And but the problem is that when he wrote a manuscript, and he said, okay, the manuscript that follows, which he finally published in 2004, the manuscript that follows was written 15 years ago. I just wanted to justify my proposed definition by checking that all known examples of CFTs did fit the definition. This task held me up. So, I mean, in these axiomatic approaches to conformal field theory, which that were written, by Segal, by Kontsevich, etc. The problem is you have to find examples. And so today's talk, or our program, so you only get a glimpse of what we did, but I mean, of all the issues behind what we did. But today's talk, it was about, well, defining one CFT through the path integral, the Liouville CFT, and when I say defining it, I mean in a non-perturbative way. That's an important point. That probability theory enables you to give non-perturbative definitions of path integrals. So I'm going to try to explain how we define a path, the Liouville path integral. And then I'm going to state kind of what is the Liouville conformal bootstrap approach. And what we did is show that they're both the same. And the key to showing that all these objects that appear in physics, the conformal bootstrap approach, so the conformal blocks or Nekrasov partition function, etc., they have a probabilistic equivalent, exactly. So we're mapping probability theory to representation theory, and we're doing that by showing that the probabilistic object we defined does give an example, a concrete example to Seagal celebrated axioms. So, and by the way, so I didn't understand everything in the first talk this morning because it's not exactly all my language, but there was the word topological quantum field theory, and sometimes when you read it like Wikipedia, you read it's the Atiyah-Segal axioms, and they were inspired by these axioms on conformal field theory from Segal. So let me try to explain to you what these axioms are before I define so the Segal axioms. So if you want to construct a conformal field theory, so it's very natural. So when you have a surface with marked points, so you associate correlation functions. Now and in Segal's approach, what you have is you define amplitudes. So I'm going to explain. So what is an amplitude? It's a Riemann surface with boundaries. So what you do in Segal's approach, so these are his axioms. So take say this Riemann surface. Okay, it has 3 boundaries, and let's say it has 1 marked point. Okay, I'm going to take this one. But okay, give you an example. And on each, so when you have a Riemann surface with boundary with charts, you can always parameterize with a circle. Okay, so on each boundary, you put a function from the circle into the real line. So S1 is my circle. Okay, so and what you do is you have an amplitude. So when you want to construct a conformal field theory in the sense of Segal, well, so my surface it has a metric, and it has a mark point, and it's not a number when you have a boundary. See, when you have no boundary, it's just correlation function. This is a number. I mean, belongs to R. But if you have a surface with a boundary, in Segal's approach, what you do is you associate to each boundary a function. So it depends on 3 functions from the circle to the real line. It's called an amplitude. And actually on each space of functions from the circle to the real line, you put a measure. It's a Hilbert space. So it's an L2 with respect to some measure mu0 d phi. Okay? And it's very natural, the axioms of Segal. So first, I'll write it more precisely later, but on your correlation functions, you put 2 natural assumptions. So it's the way the theory is going to react if you take a diffeomorphism of your surface, and if you change your background metric by a conformal factor. So I'll see later precise definitions, but you need 2 kind of assumptions on your correlation functions. And if you really want to accomplish, Segal's program of constructing a CFT, there's this third assumption, which is very natural, and it's here. So you have your amplitude, so your surface, say, with 3 boundaries, and you have another one, say, okay, so take another amplitude. So I'm going to take, okay, something like this, another one. So I'm going to take, say, one mark point 2, and so it depends on. And on the boundary, I put 3 fields. So now I'm running out of chalk. Okay, okay. And so you see, I have my space. Okay, and I have. So it depends on this. Okay, my second. So I have my second Riemann surface. So it has a metric G2, a marked point x2 alpha 2, and it depends on my data on my boundary, which is 3 functions defined on the circle. Now, Segal's axiom, it's a natural gluing axiom. It's just this, is I take my two Riemann surfaces. So I suppose, okay, that the 2 metrics can glue together rather nicely. So you glue your 2 Riemann surfaces, and you just say that your amplitude, well, it's just the composition of the 2 amplitudes. So you glue your surface. This is the third axiom. The 2 first ones I'll give him later, but so my Riemann surface now, I glue my 2 surfaces. So it now has 2 marked points. 1. Okay, so this thing. Now, if I glue my 2 surface, it has 4 boundaries, right? Because I'm gluing 2 boundaries. So it depends on phi 1, phi 2, phi 1 tilde, phi 2 tilde. And this is equal, so sorry, I'm going on the next board to get to some. So this is this amplitude. So this is equal to just, I integrate my two amplitudes up there. So let me put implicitly G1 in the metric. It's just my two amplitudes that where I fix the two fields equal. Okay, so see I take the two, and I integrate with respect to my L2. I put a measure on my space of functions, and so I just integrate my two. So when it's just I put natural Hilbert space on each boundary, and when I glue my surfaces, I'm taking, if you're doing operator algebras, I'm taking what is called the partial trace. If you're doing probability theory like me, you're just writing down what is a Kolmogorov-Chapman equation. The way Markov kernels they glue, and it's just a generalization to Riemann surfaces of what you learn in standard textbooks when you do probability theory. So okay, so I think to summarize, I'm going to try to explain today in the few time I have, so how we construct a path integral. Then, okay, we're going to admit, but then we showed that this path integral somehow it satisfies these gluing axioms of Segal, and thanks to that we were able to show that the correlation functions of our probabilistic object, they are exactly equal to the conformal bootstrap, which is written in the physics. And along the way, we're going to end up with problems that physicists don't talk about. And so I'm really happy when I talk to physicists to know what they think about these problems. And I get usually different answers. So according to how much they feel close to math and how much they don't. So it's always an interesting game to talk to physicists. And also I would like to highlight that lots of the ideas that we implemented are due to, in fact, we were highly inspired by physicists, and in particular, Jörg Deschner had a great role in all this work we've been doing the past 7-8 years. His ideas, I mean, some were really brilliant, and we used them. Okay, so what is so now let me jump to Liouville. So Liouville is a path integral, so I have my Riemann surface with my metric up there. And I want to look, so I'm on my surface and I want to look at the function at this following volume form on the space of functions from my surface to R. So what I do is I take the uniform measure on the space of functions and I reweight by the exponential of minus the Liouville action. And so when I have my function, there's the standard gradient square term on my surface, plus, so Q times the curvature. So this is the Ricci scalar curvature times the function phi, plus what is interesting, the interaction term. So I rewrite the mu exponential to the gamma phi, and I integrate this on the volume form of my surface. So Liouville is about defining this thing, okay? And so it was introduced by Polyakov in '81 in his paper on bosonic string theory. So the theory depends only on it depends on two parameters, because Q is given by gamma over 2 plus 2 over gamma, so it's redundant, and actually it really depends on one, because parameter mu it can be scaled out. I mean, for different mu's, all the theories are at a scaling factor. They're the same. So it's really a theory. So here I put gamma in 0, 2. This is because I'm doing probability theory, and we're going to define this object only for gamma in 0, 2. Of course, I mean, in physics, they write it for all gamma. But if you want to enter this field via probability theory, we need to restrict the value of the parameter. Okay. So we want to define this object here. And the problem is that this thing is not defined. The Lebesgue measure on the space of functions is not a well-defined object mathematically. However, one thing is defined is we're going to, if we integrate this gradient square term, probability theory is now going to help us define this object. Okay, so let me introduce the Gaussian free field. So when I have a Riemann surface, so the Gaussian free field, I should have wrote in the slide. The Gaussian free field, when I have a Riemann surface with a metric, I have a green function, okay? So the green function, it's just the inverse of the Laplacian, okay? So the Gaussian free field is just a Gaussian, which depends on whose covariance function between 2 points is given by the green function, I'm going to call it this way, on my surface. And what is the green function? It's just the inverse of the Laplacian. So I put a minus, it depends on your convention on the Laplacian. But if the Laplacian is not positive definite, you take minus. Okay, so if you want to inverse the Laplacian, you get the green function. And the Gaussian free field, it's nothing but this thing here. It's a Gaussian which lives on the surface. And okay, and here's a concrete way to construct it, is you take a standard sequence of Gaussian variables, and you take a orthonormal basis of eigenfunctions, okay, associated to the eigenvalues lambda n, and you take it of average 0 on your surface, and you take this infinite sum here. So and then this gives you a Gaussian variable whose covariance is given by the green function. And then what you do when you do so as I told you, you can define this volume form d phi. Okay, so what you do is you stick in the idea is that you can define d phi, but you can define d phi times this term, and it's the Gaussian free field xj. So if I want to compute a functional of phi against this thing, well, the rigorous math definition is on the right. So what is it? I take the Gaussian free field, but there's a twist. I add a constant according to the Lebesgue measure. Okay, so if I okay, for norm, you can forget about this term. There's a determinant of Laplacian hanging for normalization issues, but I mean all the interesting stuff is here. And what I'm doing here, by the way, it's general. I mean, if you want to do quantum field theory in dimension 3, 4, 5, 6, what you do is you say that this term here is nothing but the Gaussian free field. So the thing is that you see what's interesting with probability theory is that, I mean, if in any quantum field theory, you can attack it in some sense by probability theory, because you're always going to have this quadratic term here hanging. Okay, so we write this definition, and then the idea, well, it's fairly simple, is that, remember Liouville. So you had Liouville, so it was integral of d phi square plus, so let's say q curvature phi plus mu e to the gamma phi. Okay, and so you rely on your Gaussian free field. You cut your integral in two, right? You take this piece and so you put it with d phi. So you write it like this, right? Okay, times e to the minus. So there's a 1 4 pi, I think. Never mind the 4 pi. And you see you have this d phi squared, d phi. And remember, this I said is the Gaussian free field plus constant, okay? Gaussian free field plus a constant. And so to construct Liouville, you just treat this term as a Radon-Nikodym derivative, in theory measure, with respect to something that you have that is well defined. And you're always going to do this anyways in quantum field theory. So it happens to work well with Liouville. And so we do that. And so we get a definition of the Liouville path integral. We define everything with respect to the Gaussian free field. And here you have your your term here, which is what I wrote downstairs, it's your Hadon-Nikodym derivative. Okay, and so there's an extra problem, which is cured nicely using probability theory, that usually when you do that, you know, the Gaussian free field is ill-defined. You know, it's because, you know, what is the green function on a surface? It's essentially the log of the difference, okay, plus terms. And so it's an ill-defined field. You can't take the exponential. So what you have to do is I'm writing stuff under the rug, etc. But what you do is to define the exponential. So the exponential is the interaction term, okay, here. What do you do? Well, you regularize your field to some scale epsilon here, and then you renormalize, you introduce a counter term, you go to the limit, and okay, probability theory here saves the day, and it shows that it's well defined. And here's the issue: if gamma is in 0, 2, well, this random volume form, it converges to a volume form on your manifold, but it's non-zero if and only if gamma is in 0, 2. So if gamma is outside 0, 2, probability theory will not do the right thing. So, but if gamma is in 0, 2, you get a well-defined object, which is called Gaussian multiplicative chaos, which was introduced by Kahan in 85, roughly around the same time Polyakov introduced his path integral. But you know, communities don't especially communicate all the time, and so you know, it's kind of always funny to see that people are kind of working on the same object. Okay, so so this is a crash course. How do we define this object? Okay, but there's also another issue, is that if I want to take, so the correlation functions, I don't want to take just any function of my field. I want to take the exponentials. So I really want to define the integral of the product of exponential alpha I phi of xi with respect to my action. Okay, sorry, that's a metric, etc. And well, the problem is that taking the exponential of the free field in a point is also a problem. So if you want to define the correlations, you have to regularize, etc., etc. But at the end of the day, you can show that using this probabilistic approach, you can define a non-perturbative object, and that it is non-trivial if and only if the weights you put, okay. So if I take the product of the exponential of the alpha j Liouville field, so the field taken at the point xj, it's non-trivial using probability theory if and only if the alpha j's are smaller than q. So remember, q was my parameter, gamma over 2 plus 2 over gamma. And the sum of the weights is bigger than q times the other characteristic of the surface. Okay, so
I have a question.
Yeah.
So why are you saying that it will be valid? The expression for the Gaussian free field for the Liouville expression would be valid only for 0, 2, because the Radon-Nikodym derivative would be still applicable, right? For that.
I don't understand. So I said, I mean, what exactly?
Why would you go back to the previous slide?
Yeah.
Yeah. So you're saying that this would be valid only for mu greater than 0.
Yes. Mu is bigger than 0.
Gamma belongs to 0, 2, right?
Mu is bigger than 0.
Yeah. Now, I mean, in general, it would be valid for any gamma, not just belonging to 0, 2. Why should it be valid for only gamma belonging to 0, 2?
Well, because, okay, so you want to take imaginary gamma, for instance?
No, I mean gamma.
If you take complex gamma, you're in trouble, okay?
No.
Because
beyond the range of 0, 2. Real, but beyond the range of 0, 2.
Yeah, but if you go beyond 2, you're going to get 0 here. This converges to 0. And so it converges to 0, so it gives you Gaussian free field theory and no longer Liouville. So that's the problem. Okay, maybe. I don't, maybe, okay, is it, I don't know if I understood your question, but the entrance is really via 0, 2, because otherwise probability theory gives you the wrong answer.
Sorry,
That's
I
the-
actually have a comment to the same point. I was wondering about it when you first said it. I think I understand what you're trying to do in terms of probability, trying to keep it constrained between 0 and 1. But my first point I was thinking is, why did you even choose Q as a value to do it for? And the second point is, from the physics point of view, there are examples from quantum mechanics where it goes outside of probability. They're just physical interpretations for it. So maybe that's just something to consider.
Yeah, but I mean, that's the point, is that what we're going to discover is that we're going to match with the bootstrap. And so, so by analytic continuation, these objects we have can go outside. It's just that we don't know if probability theory if there's a probabilistic interpretation outside of these ranges.
And why Q? Have you thought about some other variable to constrain it for?
Oh, you mean not gamma over 2 plus 2 over gamma?
Yeah, just some other
Oh,
one.
it'll give you a quantum field theory, but it won't be a conformal field theory.
Ah, okay. So, okay, fine. Thank you.
Yeah, I mean, if you take Q outside, you get a quantum field theory, but it's not conformal. I mean, it's like when you're doing a Riemann surfaces, the classical Liouville action is a bit different. Okay, and you need to put in the right value in order for you to get a conformal factor. Okay, because in fact, this Liouville field is going to be a random conformal factor, and you need this. Okay. So, okay, and so what was interesting for us, and this is okay, maybe some kind of thing we try to say to physicists that make. So at the end, okay, when we play around, we actually get something rather explicit. I mean, we get, okay, the average. So E is my average with respect to my Gaussian free field. We get the average of a kind of weird random variable, okay, which is, integrating on my surface, my random volume form, my random Gaussian multiplicative chaos. But so this is the green function, remember, but with a Hadron-Nikodym derivative. And so it gives you some kind of completely probabilistic formula for these correlation functions. And one thing is nice is that what we can do extends to Toda theory, okay? And for instance, in Toda, there are several fields, and then you get several variables here, and then you get a really clean math definition of what is the correlation functions in Toda. And since in physics, there's no general formula for the 3-point function, this provides a way of really having a complete definition, a completely rigorous definition, which you can simulate, by the way. You just do Monte Carlo. I mean, on Gaussian free field, we've done it. It's maybe not as efficient as Bootstrap computations for Liouville, but it works. Okay. So okay, so we get this up to some factor, which depends on okay, which is completely explicit. Forget about this B. Up to some factor, it's just the average of a random variable. These correlations in Liouville, and in Toda, etc. So we have so good. So we were happy. We had a way for us to understand what is the correlation functions in Liouville. And then, of course, well, we said, okay, so we kind of opened the door. Now let's see what's in the shop. And so you go see physics, and physics, they have tons of formulas all over the place. And they have all this bootstrap, etc. formalism. And so that's what we did for the past 3 or 4 years to show that these formulas we have, okay, this probabilistic formula we have for the correlation, it matches what physicists say on Liouville when they do the so-called conformal bootstrap. Okay, and so so before explaining in the last 5 minutes what we proved, let me just say that what we did is that so we introduced more than correlation functions. We introduced amplitudes that I wrote here. We introduced Liouville on surfaces with boundary, and we showed that they satisfy these gluing axioms from Segal. And we showed that our correlation functions, they satisfy also 2 natural assumptions when you take the correlations at points where you change according to a diffeomorphism of your surface, you get the same thing where you have changed the background metric by its push forward. And we showed what is essential, the local scale invariance, which is really the strong statement on conformal invariance, which says that if I take my, sorry, well, it's not a typo, but I call the points now Zi and not Xi, but never mind. If I take my correlation functions and I change my background metric on my surface by a conformal factor, well, it moves like the determinant of the Laplacian, okay? Meaning that, okay, you get the same thing up to the exponential of my conformal factor times what is called the conformal weight. And the conformal weight is explicitly given in Liouville by this formula. And times, so the term which is here, which is exponential, the central charge, so it's a number, times what is called the Liouville action also. It's, it's a co-cycle and when you do Riemannian geometry. And the conformal weight is given by what is predicted in physics, 1 + 6q². Okay, so to answer the question, you won't get local scale invariance if you change the value of q. If you take a random q, I mean, not gamma over 2 + 2 over gamma, you won't get this property for your theory. Okay, so now that we have our theory, which satisfies lots of natural geometric rules, we can show it's equivalent to the bootstrap. Okay, so what is the bootstrap? So first, if you want to understand the bootstrap solution, what you do is you have to understand the 3-point correlation function of your theory. So you put yourself on the Riemann sphere and you put a background metric, say the round sphere. Now, thanks to these axioms I wrote, you can always play around with your points using Möbius transforms. And so all these 3-point correlation functions up to trivial factors are nothing but the 3-point functions at 0, 1, infinity, taken at these points on the Riemann sphere. And so in physics, they had a prediction for this from the bootstrap, and it's called the DOZZ formula. So this is what we proved. So it took us quite some time. We proved that our probabilistic 3-point functions, so this average of a random variable, it's given by this crazy formula by Dorn, Otto, Zamolodchikov, and Zamolodchikov. That's why it's called DOZZ. So, it's a crazy function from, analytic number theory. So, and then we started proving the higher order correlation functions. So you take the 4-point function on the sphere. So your Riemann surface is the Riemann sphere with the round metric, and you want to know what the correlations are at 0, z, 1, infinity. Okay, because by conformal invariance, you have 3 degrees of freedom, so you can always map your 4 points to these 4 points here. So it's with one. So Riemann sphere with 4 more points is dimension 1. Its moduli space is dimension 1. And what we did is, so we did this in 2020. We showed that we recover these that are probabilistic, our averages. They're equal to this complicated thing. So a product of DOZZ type formulas times these, kind of mysterious holomorphic functions, which are called the conformal blocks, or we know now, thanks to AGT and all these works, that these things are the Nekrasov partition functions. Okay, and one thing that, so this is one thing, so we have this theorem, and we tell physicists, okay, but we have a completely indirect proof that this thing exists. Okay, why? Because look at the definition of a conformal block. I mean, it's kind of crazy. So I'm not going to give you any details because I have 2 minutes left, but it's completely non-explicit. And even with Nekrasov's expressions, I mean, it's very complicated. And I don't know. So as an output of our work, this thing has a radius of convergence given by 1 in the z variable. Okay, it's a holomorphic series. And I know no proof without this completely indirect proof. I know no proof of this fact that a holomorphic block, it exists, that the series converges. So we have a proof, but it's indirect. I mean, but I don't know if someone knows by hand showing that this has radius of convergence 1. So this is an output of our work, and so there's also this so-called crossing symmetry. We show that if you flip, 2 points and 2 weights, you get always the same thing. And this is exactly what bootstrappers do, and we'll probably see an instance of this tomorrow, is that they assume that there's this invariance. And when you flip, you flip z to 1 minus z, and you flip your weights accordingly, you get the same theory. So it's called crossing symmetry. And so we get an indirect proof also of this fact for the conformal blocks. And okay, as far as I know, there's no proof of this completely rigorous proof. Okay, well, I'm going to finish in a minute just by saying, okay, I showed you that, okay, we proved that our stuff, the 3-point function on the sphere is the same, the 4-point on the sphere is the same, and then we actually proved that on any Riemann surface, if I look at the conformal bootstrap, what you expect from it, and you compare with what we have. So, on any Riemann surface, you can put natural holomorphic coordinates, which are called plumbing coordinates. So I'm on the moduli space of a Riemann surface of genus H with M marked points. You can put natural coordinates called plumbing, and we can show that they match these conformal block, these holomorphic functions which appear in the physics theory. Okay, so, and to do this, so this is what I wanted to say. To do this, it's what I said a bit earlier. You take your Riemann surface and you cut it into pants, and then you know that you can once you cut it into pants, you can decompose your correlation functions using these gluing rules. You can just say that on your surface, you just glue according to pants, and you have Segal's axiom. And then once you have Segal's axiom, what you do is you project in this natural Hilbert space the L2 space associated to this measure. So you do spectral theory on this L2 space, and it gives you all these conformal blocks here, and all these conformal blocks up here. Sorry, here. And you get times the product of these DOZZ formulas. Okay, so I won't go that much into the detail, but I'm just going to finish with applications. So what we did here, we are going to do it on open surfaces. We're going to do it on for TODA conformal field theory. So TODA is when you have lots of fields, not just one exponential, but lots. Let me say also that recently, thanks to our results and so-called conformal welding results, a group of people in the US are giving sense to imaginary DOZZ formula. So what would be imaginary Liouville? So when gamma is purely imaginary, and so they're now recovering formulas from physics in this context. The last thing I wanted to highlight, which I find really very nice, I at the beginning, I was really thrilled by this paper by Gozal, Remy, Sun and Sun, is that Liouville correlation functions, what we kind of discovered is that they have a clean probabilistic definition. So there's a probabilistic content to this stuff. And they discovered that the conformal blocks themselves, these building blocks, not just the correlation functions, so the Nekrasov partition function can be seen as the average of a random variable. And so this enables them to show lots of results on convergence also. And this, I think, is nice because it means that you also have a direct probabilistic formula for these for the blocks. So remember, the blocks are, so if I look at the 4-point, it's the building block. So we have probabilistic formula for the correlations, but they also, so now they've discovered there's a probabilistic formula for these things here, for the blocks which enter the bootstrap formulas. Okay, so I'm finishing with just the references. So it's what I said today is based on tons of papers. Actually, it took us lots of time. And so if you're interested, there's all these papers are now roughly published. So thank you for your attention.
Okay, so I saw this slide about integrability, and I was going to ask something about integrability of this theory. But first, I'd like to know what these abbreviations are in the last slide, the previous one. Yeah, what is SLE of CLE? Yeah.
Oh, sorry, integrability for SLE or CLE. Sorry.
Okay, Or you mean?
Ah, or, sorry, it's a typo.
Okay, but I don't know what any of these things
Ah,
are.
okay. So, yeah.
Maybe you all know.
No,
but
it's
I
great.
don't.
It's great because, you know, when I come here, it's like, so this is do I have something to erase? So, okay, so thank you. So SLE is, okay, so this is the, you know, one of the big breakthroughs in probability of the past 30 years. It's SLE is Schramm. You know, Schramm, oh, I don't know if there's one M or two M's. I forget always.
These are names, right?
Yeah, Schramm-Levner evolution. And CLE is conformal loop ensembles.
Right.
And it's, in fact, it's just a different way in some sense of seeing things. So in physics, people look at fields, which are conformally invariant. So what I talked about. And what Schramm introduced is random curves. And so he introduced you know, you take 2 points in a domain, and he introduced all the random curves which are conformally invariant between 2 points. And then what Sheffield did with Werner, he introduced the same thing but for loops, random loops. See, when you have random loops, you can look at observables, which are conformally invariant.
Right.
And recently, what these guys proved is that if you take the 3-point function of these loops, so roughly you look at how many loops are around 3 points, you get the imaginary DOZZ formula.
But what does it mean? What does integrability means in this context?
Oh, it means you get, okay, it's very loose. Okay, I may be overselling things. It's very loose sense. It's just saying you can compute things.
Okay, solvability.
Yeah,
Okay.
yeah,
But,
okay, maybe.
Is this, so as far as I understood, you kind of computed the correlators and tried to solve this Liouville two-dimensional field theory, right? Conformal field theory, or not?
We gave, we showed, we gave a probabilistic content
Right.
to this thing. And in passing, it enables us to show that the bootstrap is coherent.
Right. But is this an integrable field theory somehow?
A what?
An integrable field theory?
An integrable field theory?
Yes.
Why?
The
I
notion
don't
of
know in what
integrability-
sense. I mean,
oh,
it's
because there is the notion of Liouville integrability, but now you have a
no,
Liouville.
it's not Liouville. I mean, it's
not.
it's integrability in the sense of bootstrap. I mean, that you
Right.
have special functions and. Yes.
I have a question. Sorry. Shall I go ahead with my question?
Yeah. Okay.
Yeah. So you said that the correlation functions vanish for gamma greater than 2, right? Because of that epsilon factor.
Yes. It's going to.
But they would if you take epsilon goes to 0, it would vanish for any gamma greater than 0, right?
If I understand, so you say any gamma greater than 0.
Yeah. So if you have epsilon,
if I
to the
take
gamma square by 2, then for any
no, if I
epsilon,
take gamma equal 1, okay, say I take gamma equal 1, okay?
yeah, then it would be epsilon to the half. It would still be 0 to the. Okay, so
No.
0 to the half.
No. Here so no. I mean the correlation function. So I just stick in the exponential here. Exponential to show the different points, and I renormalize, blah blah blah. Here, same thing. I renormalize. I go to the limit. I get something which is well defined, and so sorry. In my theorem, gamma has to be in 0 too. Okay, but if I take
yeah, but if you can you go back to the previous slide?
Oh, previous, yes.
Yeah. So here epsilon, if you take the limit epsilon goes to 0, epsilon gamma square by 2.
Yes, this thing.
Yeah, then only for gamma equal to root 2 do you have 1. Otherwise, you don't have 1. You have some other factor. right?
Yeah, I need this bound, yes.
No. So for instance, if gamma is 2, for instance,
If
then
gamma
it
is 2,
if there
okay, if
it
gamma
would
is
be
2, if gamma is
then it
2, this
would be
converges to
square.
0.
It would be 0, right?
Exactly.
So then even for gamma equal to 2, it wouldn't hold.
It will
Well,
work because I'm not talking about this case. If for gamma, okay, okay, I can take gamma equal 2 because here, okay, okay, so this is something I need to, it goes to 0, but for gamma equal 2, I can, this is how I define my limit. Okay, for gamma equal 2, I give an extra push by square root of log. And then I can define all Liouville and do everything. It's just I didn't want to talk about this case.
Maybe we should move to the next question.
Hi, sorry, I just wanted to, I just didn't understand how would you define an amplitude in that you define a path integral,
Yeah.
but the path integral is, well, I guess it's defined when it's compact and.
Yeah, but in amplitude, it's okay. It's going to be the same definition, okay, except that I'm not going to take my Gaussian free field on my surface. I'm going to fix the boundary fields, and I'm going to take the Dirichlet Gaussian free field plus the harmonic extension of my boundary fields, and I can define the exponential, blah blah blah, and it works the same. It's actually simpler to define an amplitude, but I can show you. I mean, the definition.
Yeah, because when usually in quantum field theory, when we define these things, we use the Probabilistic quantization. So we take the Gaussian part. We just assume that it's like finite dimension integral and just determinant and so on.
Yeah.
So it only works when there's no assumption on boundary condition.
Yeah, so I don't know. I'm not that familiar with the BRS. Yeah, the
BRC.
yeah. I wouldn't know. In our case, it doesn't set a problem. The amplitude.
Yes.
It's just replacing the Gaussian free field on your surface by Gaussian free field with boundary conditions, but given by my boundary fields, and then you're good.
And another question I was wondering, string theory is not included in these parameters, right?
What? What is not included in the parameter?
String theory.
String theory?
Bosonic string theory.
Oh, no, because the 26 dimension thing. You mean?
Yes.
No, but it's 26 is okay. What is 26? It corresponds to a central charge of Liouville 0. It corresponds to no Liouville. Okay, if you're not in dimension 20, so here you're embedding in some kind. Gamma equal 2, it's 2D string theory. It corresponds to, that's why gamma equal 2 is important. It corresponds to embedding in dimension 1. But if you embed in dimension 26, your string, then there's no Liouville. Exactly, yeah. Question? Okay.
So usually the 4-point, the 3-point function whose expression you showed is computed by studying a 4-point function with a null field in the 4-point function.
You mean in the Bootstrap?
Yes.
So in the Bootstrap, they write this. Okay, the Bootstrap they write
expression for the 3-point function that you showed.
Yeah, they do this.
Exactly.
That's the Bootstrap. That's how they compute numerically this thing. Okay.
Well, usually, because this is an integral equation, one picks one of the fields, let's say alpha 4, as a null state, so that the integral is now a finite sum on the two sides, and
Yeah.
one can then use some hypergeometric functions to solve these. I was just wondering, are these null states somehow special in the formalism that you have used? Like, are there, because the fact that they are null states have to do with the Virasoro algebra, and from what I see, that has not played a role in whatever you have done. So I just was wondering if there is a link between these two things.
This is because I'm not this is because I don't have time, but the Virasoro algebra plays a huge role in what we do. It's because what we do is by Segal, we end up with doing spectral theory on some L2 space of functions on a circle. And what we do is to recover the formulas, we have a probabilistic construction of the Virasoro algebra acting on this thing. Okay, this is a Hilbert space, and on this Hilbert space, we have the Virasoro algebra acting, and we show that it diagonalizes, any function. And so that's how we recover all the. I mean, of course, we have a Virasoro algebra acting, because otherwise we couldn't show that, we couldn't recover these blocks, right? Because the Virasoro algebra is completely hidden in this Shapovalov business. So yes, we have the Virasoro.
Are there such things as null states in this whole?
So in Liouville, yeah. So there is a null state. It doesn't play that much of a role. I mean, it's just that maybe this will talk to you. We really decompose our Hilbert space. Okay, so this is our L2 space. A space of function on a circle. We really decompose it in Fermat modules. And and the Virasoro algebra acts on each of these things. I mean, 45 minutes.
Okay, well, thank you very much. We are going to reconvene after lunch.
Okay, thank you.